Next slide. This slide shows the triangular relationship between the apparent magnitude, or the apparent brightness, of an object, and the distance of the object, and the true power output of the object, called the luminosity. The luminosity is the total amount of energy emitted by the object every second. It's wattage. In the textbook, I talk about intrinsic properties. Intrinsic means belonging to the object by its very nature. It does not depend on its environment or where the observer is. Luminosity is an intrinsic property. A 100-watt light bulb gives off 100 watts of light regardless of how far away it is from us. Back to the triangle. If you know two sides of the triangle, you can find the third side. For example, in the inverse square law, if we measure the apparent brightness of a star, and we know its actual wattage, that is, its luminosity, then we can derive the third part of the triangle, the distance. Next slide. This shows the triangular relationship between the luminosity and the two things the luminosity depends on: the object's temperature and its size, its diameter. Let's look at the temperature of stars first. The color and luminosity of a star depends on its temperature. The color of a very hot star is blue, and the color of a very cool star is red. A more precise way to measure the temperature is to take the spectrum of a star, find at which wavelength the brightness or intensity peaks, and then use Wien's law, which says that the temperature equals 2.9 million divided by the peak wavelength given in nanometers. That is a labor-intensive but accurate method, while just looking at the color is a very quick but imprecise method. A melding of the two methods is to use filters. The blue and yellow-green filters are the standard ones we use to quantify a star's color. A hot star is brighter in the blue filter than in the yellow-green filter, but a cool star is brighter in the yellow-green filter than in the blue filter. Slide. The luminosity depends on the temperature and the size, or the surface area. So to measure the size of a star, if you measure the temperature and the luminosity of the star, you can derive the size. This is the quickest way to get an approximate diameter for the star. For example, the red star Betelgeuse is pretty cool, temperature-wise, but it is also very luminous, which is why we can easily see it from the middle of Bakersfield, even though it is over 220 parsecs, or over 720 light years away. To be so luminous, it must be very large in size. In fact, it is a supergiant that if placed in the center of our solar system where the sun is, it would swallow all the planets out to Jupiter. Because of the luminosity temperature size interdependence, a small hot object can have the same luminosity as a large cool object. So if the luminosity remains the same, an increase in the size, that is the surface area, of the object must result in a decrease in the temperature to compensate. Next slide. This slide shows a much more accurate way to get the size of a star. Use an eclipsing binary system, which is two stars orbiting each other in a plane that is parallel or along our line of sight. We'll see one star pass in front of the other star, partially or completely blocking its light. We time how long the eclipse takes, and if we know the speed of the stars in their orbit from the Doppler effect, we can get the diameter of the star, which is equal to the orbit speed multiplied by the eclipse time. Next slide. Speaking of star velocities, the motion along the line of sight is measured with the Doppler effect. Recall that if the object is moving towards you, its spectral lines will be shifted to the blue, to shorter wavelengths because the waves are scrunched up. If the object is moving away from you, its spectral lines will be shifted to the red, to longer wavelengths because the waves are stretched out. A faster speed creates a greater shift in the wavelengths. Next slide. The motion of the object in the perpendicular direction across the sky is measured from the proper motion, which is the angular distance an object moves in a given amount of time. If you know the distance to the object, then you can convert the angular speed to an actual linear speed. Next slide. Put the Doppler shift and proper motion data together to get the total three-dimensional velocity. This picture shows one scenario where the two stars have the same Doppler shift, but their total 3D velocities are very different. We use the star's total velocity to measure the amount of mass, including dark matter, in the galaxy and how the mass is distributed. Next slide. A planet's mass is measured by looking at the motions of satellites orbiting the planet. Stars are much too far away to see planets orbiting them, so we look at those stars that have another star orbiting them in a binary system. The two stars orbit each other around a common point. Fortunately, the majority of stars in the galaxy are in binary or multiple systems. The more total mass there is in the system, the greater is the gravitational acceleration of the stars. Remember the gravity stuff from Chapter 5 of the textbook? The animation shows that the binary system with more combined mass has a shorter orbital period. Next slide. The two stars orbit each other around a common point called the center of mass. The center of mass is the point the stars would be balanced upon if the stars were on a stellar seesaw. The massive star is proportionally closer to the center of mass than the low-mass star. The ratios of the masses is the inverse ratios of the distances each star is from the center of mass. The animation cycles through several examples. In all of the examples, the stars are 20 astronomical units apart from each other. Next slide. Most binary systems are too far away to resolve them, that is, see them as two individual stars, but their periodic Doppler shifted lines give them away. These are spectroscopic binaries. We use the Doppler shifts, i.e. the velocities, of each star to derive their individual masses. Both stars remain directly opposite each other as they orbit the center of mass, with the center of mass always between them. The two stars have the same period, so the more massive star with a smaller orbit must be moving proportionally slower than the less massive star. Their orbital period gives us their total combined mass, and their individual speeds enables us to proportion how much of the total mass of the system goes with each star. There are two caution paragraphs in the star mass section of the textbook. Pay attention to them. One is to remember the distinction between star size, the diameter, and the star's mass. A star's mass is not necessarily related to its size. The other is when comparing two separate binary systems of the same separation distance, the two stars in the binary system that has a larger combined mass will move faster than the two stars in the binary system with less combined mass. The larger combined mass binary has a greater gravity force acting between the two stars. However, when comparing the two stars within a particular binary system, the larger mass star will move slower than the less massive star. The gravity force acting on the two stars within the binary is the same, equal and opposite, for both of the stars.